Good morning, everybody. Today's structural analysis class, we are going to see a method that is slope deflection method of structural analysis. So in this method, in this class, we will see how to find out the forces using the slope deflection method. So I'm going to start the slope deflection method. Slope deflection method. Before proceeding to the details of this method, we will see some of the core points later with this method. So this method of slope deflection, that is slope deflection method, comes under stiffness or displacement or equilibrium set of method of structural analysis. So this method is suitable when the degree of kinematic indeterminacy is less than the degree of static indeterminacy. So basically in this method, the joint displacements which are the slope theta and the deflection delta are taken as unknowns, and using these two unknowns the forces are found out, are taken as unknowns. Also in this method, the axial deformation is neglected. Axial deformations of the structure are neglected, and this is of course one of the assumptions of this method. So using these two unknowns, that is theta and delta are taken as unknowns, as I said. So in order to find out these two unknowns, to find this theta and delta, joint equilibrium conditions are written. Joint equilibrium conditions and also shear equations are written. Shear equations in case of frames, these are written to find out theta and delta, and finally the forces are found out, are written. Finally, to find the moments at each span, force displacement equations are written, and these force displacement equations are also called as the slope deflection equations. Force displacement equations are written to find out the equations are written to find out the moments, and these force displacement equations are also called as the slope deflection equations. So I will quickly try to derive the slope deflection equation. So we will consider a span, continuous beam having 3 spans, and we will try to derive the slope deflection equation. Derivation of slope deflection equations. So this method of the slope deflection method is basically developed by a scientist called as G.A. Manny. So I am considering a continuous beam having 2n fixed, and there is a span AB in between. So let it be OC, and let a point load act in the span AB at a distance small a from A and small b from B. Okay, so basically for in the entire slope deflection method, the sign convention followed is sign convention. The clockwise moments are taken as positive and the anti-clockwise moments are taken as negative. This is in case of end moments. The clockwise slope are taken positive and the anti-clockwise slopes are taken as negative. This is for the slope theta. So we will see other sign conventions. For example, if the beam is there is a settlement, there is a relative settlement in any of the span, we will see how we will follow the sign convention. Okay. So initially for derivation, the step one involved is I am considering a span. Consider the span AB. Consider span AB. So due to the load effect on A, as the figure implies, there is a point load acting on the span AB. So due to this load effect, the end moment M bar AB developed will be equal to minus PAB square divided by L square. Let the length of the span AB be capital L, that is A plus B. That comes out as a summation of the two distances A and B. Also, the moment M bar BA would be positive P A square B divided by L square. Okay, we will go to the second step. Step 2 as a part of the derivation of the slope deflection equation. So as we have applied a point load in the span AB, due to this loading in the span AB, that let the rotation at NA, let the rotation at NA be theta A. Due to this rotation theta A, the moment developed at A, the moment developed at A will be equal to 4 EI upon L theta A. So this is the basic fundamental formula of the structural analysis. When a moment is the moment generated due to the rotation at that particular n is 4A upon L multiplied by the corresponding rotation. Subsequently, the carryover moment that is developed at the end B will be this in turn will give rise to the carryover moment. Due to this moment developed at end A, the carryover moment developed at B will be equal to 2 EI upon L theta A. So next we are proceeding to the step 3. Similarly, we will consider the support at B, continuous support at B in the span AB, or the joint B, not exactly the support, it is a joint B. So let theta be the rotation developed at B due to the end moment. This is the rotation developed at end B. The moment developed, so going by the same fundamentals as we did in the step 2, at B will be equal to how much? It will be exactly equal to 4 EI upon L, but here the rotation will be theta B. So similar to the carryover moment which was developed at B due to the moment developed at NA, here due to the moment at the joint B, there would be a carryover moment, but now it is developed at the joint A, and this will be equal to 2 EI upon L multiplied by theta B. So this is the step 3. So finally, we will move to the step 4, where we are giving on possibility of settlement. So in the continuous beam, if delta is the relative, or theta is the settlement between relative settlement between A and B, joint A and joint B. Then the fixed moment developed at A, if theta is a settlement between relative settlement between A and B, then the fixed end moment at A will be equal to minus 6 EI theta divided by L square. Similarly, at B also it will be equal to minus 6 EI theta divided by L square. So again, you will wonder how this negative sign came. So the negative moments are generally produced when this settlement theta produces clockwise rotation to the member. Suppose if the tendency of the settlement is such that if it produces clockwise rotation to the member, then the moments are anti-clockwise, that is negative. Here the negative implies the anti-clockwise moments, and how this anti-clockwise moments came, and this point gives the explanation for that. Okay. Finally, we are now in a position to sum up all the quantities which we derived in step 1, step 2, step 3, and step 4, and come to the final slope deflection equation. So the final moments developed at end A, at the joint A and B. So we will write the final moments at A and B due to effect of the above 4 steps will be, I am denoting these final moments at end A as M bar AB, or I can simply write this as, yeah, okay, M bar AB I can write. Okay, so M bar AB, which is equal to MF bar AB plus 4 EI upon L theta A plus 2 EI upon L theta B minus 6 EI theta divided by L square. So if you simplify, we will get M bar AB, which is equal to M bar MF bar AB plus 2 EI upon L 2 theta A minus theta B minus 3 delta upon L. So this is the slope deflection equation at the end A for the span AB, and this is the force displacement relation. Similarly, at the end B, we can get the final moments as M bar BA, which is equal to MF bar BA plus 2 EI upon L multiplied by 2 theta B minus plus theta A minus 3 delta upon L. So this is the, so using these unknowns, that is theta A, theta B, and this delta, we are now able to find the final moments. So this is the final slope deflection equation in order to find the moments that is developed, final moment that is developed at the joint A and B. Likewise, we will be writing the slope deflection equation separately for each span, considering the basic unknowns as the rotation and the settlement. Settlement, of course, if it is there, we will consider and if it is not there, we will not consider it. And this the theta A and theta B, the magnitude of theta A and theta B also depends upon the type of the support conditions. Suppose if it is the end span, in the end span, if the far end, if the end support is fixed, then the theta B amounts to 0. So these things we will apply, basic concepts, basic fundamentals of the structural analysis we will apply, and finally we will write the joint equilibrium equations, and we will be able to find the moments at the each span. So thank you all and best wishes.